The first talk will be given by Mark Tuckerman from New York University. He's going to talk on using machine learning to process high dimensional free energy surfaces into low dimensional paths. Mark?
Thank you very much, Amalendu, and thanks to the organizers for inviting me to this meeting. Let me grab an annotator here so that I can actually have a little pointer. Good. So it's really a pleasure for me to be able to talk about the work that we've been doing. I will say at the outset that we didn't quite get to, let's say, the killer application where I can show you an entire workflow of first generating a high dimensional free energy landscape and then being able to pick 2 points on it and actually study pathways between two interesting basins. But what I want to try to show you is what the different pieces are and where, we're employing things like machine learning and techniques like this to help us find pathways between interesting states. And I'm going to do this in the context of crystalline systems, so atomic and molecular crystals, which is where we've been focusing a lot of our efforts of late. Although we are starting to do some of this also for peptides as well, but I think given the length of the talk, I don't really have time to get into that today. So maybe at the next RARE meeting, I'll have more to say about that. The reason I wanted to focus on crystalline systems is that I think in the context of the RARE meeting, these remain among the most challenging of the rare event problems. And there really is a lot of work for us to do to be able to understand, especially molecular crystals, where you have lots and lots of molecules that may be highly flexible, and your crystals may be in non-orthorhombic space groups, and you might have high Z prime numbers and things that are really challenging industries like the pharmaceutical industry. All right, so this is an area where the kinds of simulation techniques that I'm going to be talking about are really just beginning to break through. What is our motivation for working on these systems? Well, I mean, one of the most common ones is polymorphism in the context of pharmaceuticals. Now, just to remind the audience, polymorphism refers to the ability of a compound to form multiple crystal structures. And why is this a problem and possibly an interesting thing to exploit? Well, let's first start with an area that, where this really is a very significant problem. That's in pharmaceuticals. And although everyone likes to talk about ritonavir and the AIDS drug, I'm going to talk about this drug rotigotine, which is actually used to relieve symptoms of Parkinson's disease. Now, the way this works is you form a molecular crystal with this molecule, and you grind the crystal into fine particles, fine crystalline particles. And in this case, instead of forming a tablet, you spread the particles over a patch, you apply the patch to the skin, and then the skin absorbs molecules from the surfaces of these tiny particles, presumably from surfaces where the extraction free energy is relatively low. Now, in the case of rotigotine, the pharmaceutically active crystal form is this one that you see on the left. This is now known as form 1. And it was used to make these Nupro patches. But it turns out that if you let these patches sit around, you actually start to see these snowflake-like patterns appear on them. And this is signifying that you actually have another crystalline form appearing. This is now called form 2, all right? And often the way that this happens, if it's not spontaneous, is you have a little seed of a contaminant, which in this case is the wrong crystal structure, getting into your manufacturing process somewhere, and these seeds get into the crystalline form, and it causes a conversion that may happen on a very slow time scale. Well, it turns out that these new crystals that are forming on the patches are very stable, and so they're no longer absorbed by the skin, and so this becomes pharmaceutically inactive. In other words, the drug fails. All right, and when that happens, you have to recall your drug, and you have to try to find a way to reformulate it so that you avoid this late appearing polymorph. Well, it's been estimated that there could be as many as 15 to 45% of pharmaceutically active compounds that have these late appearing polymorphs. And this is something you'd like to know about before you go to market with your drug, obviously, because if you catch it too late, then you take the cost and the PR hit of actually having to do this massive recall. Well, doing the experiments to try to find all these polymorphs can be difficult. It's time consuming. It's usually expensive. And this is an area where computational methods are sort of poised to play a really important role. But let me point to another area. This is much less known, but it turns out to be extremely important. And it has to do with contact insecticides. Okay, so my analogy for this is here's a guy walking on these beautiful crystals in a mine in Mexico. These are giant gypsum crystals. And so I call this guy a crystal walker. All right, and that's sort of a metaphor for what happens with the kinds of molecular crystals that are used to form contact insecticides. Now, DDT is an old insecticide that's been long banned, all right, but it was an interesting playground for some of the experimental groups here at NYU. Same idea applies. You take the molecule, you form a crystal, you grind it up into these small particles, and in this case, the insect walks on the particles. It absorbs the molecules through the feet or the tarsi, and they go into the insect body and shut down ion channels or whatever they do to kill the insect. Well, when DDT was used, the commercially available form was this one called Form 1. Well, my colleagues at NYU recently crystallized a new form of DDT. It's called Form 2, and it's a metastable polymorph, all right? So in this case, they're exploiting polymorphism to try to find something that may be more lethal to the insects. And in fact, you can prove that this is a more effective way to deliver the exact same compound, but in a different crystalline form. So what they did was they took fruit flies and they ran 3 trials for the Form 1 and for the Form 2. And of course, there's a control group that's not being exposed to anything. And when you watch the exposure of these fruit flies to the different crystalline forms, you'll see very clearly that those that are exposed to this Form 2 crystal are actually being killed faster than those that are exposed to Form 1. So you're delivering the same compound, but because you're delivering in a different form, you get something which has different properties. And in this case, the lethality is actually better. You can quantify this by showing, what we call lethality curves, or the fraction of flies killed at over a certain period of time. The 3 black curves here are the Form 1, and the 3 red are the Form 2. And you can see, the change or the more rapid rise time for the Form 2 crystals. All right. So this suggests that you could actually use less of the toxicant to better effect, meaning that you get more of it absorbed. And this has a kind of favorable environmental implication, right? Because if you're targeting or if you're more effectively killing your target, then the side effects of, let's say, killing honeybees or things like this will be reduced, as well as the amount of runoff that you might get of this toxic compound. So everyone knows the Ostwald rules of stages in crystal formation. The least thermodynamically stable phase is the one that forms the first. And you can imagine a corollary on lethality of contact insecticides, which is that a metastable or thermodynamically less stable phase is one that's going to be more lethal, kill the fastest. Okay, now DDT, as I said, is no longer used. So let's talk about a compound that actually is currently in use, deltamethrin. And so again, the commercially available form is this Form 1, and my colleagues crystallized this other form called Form 2. You can see it's in this non-orthorhombic space group. And when you compare its effect on the Aedes mosquitoes, which are, I think, the ones that carry dengue fever, you can see that Form 1 has an okay rise time, but Form 2 really is quite dramatic in this case. Now, unfortunately, mosquitoes are growing resistant to some of these indoor sprays, right, like deltamethrin. And this was an article that came out in Science last year, and it suggests that with this growing resistance, you need to be able to switch compounds and be able to find these interesting polymorphs. And of course, in their hands, they're very good at this. So my colleagues use this melt recrystallization technique. And in fact, for this compound here, imidacloprid, they've been able to find a whole slew of new polymorphs. So I think 1, 2, and 3 were known, and then they've generated polymorphs up to polymorph 9, which is the one you can see down here. And if you look at their effect on a variety of mosquitoes and fruit flies, you can see that, again, the form 1, the commercially available form, is okay. But if you look at these different polymorphs, especially polymorph 9, the rise time of these lethality curves is really dramatic. So it's a dramatic improvement just by exploiting this concept of polymorphism. Now, what's interesting about these crystals that you see here is that, there are different conformations of the molecule that you get in different crystal structures. And it turns out that the form or the conformation that you get in different crystal structures is not necessarily going to be the gas phase minimum for these internal dihedral angles. So this is a gas phase potential energy curve of the dihedral angles. And yeah, some of the crystals have these dihedral angles at the gas phase minimum, but some of them clearly are up the wall, right? They're not. Well, this is an example of the crystal form stabilizing conformations that are not gas phase minima. And these are very hard to find when you're doing crystal structure prediction. So let's talk about how we actually use molecular simulation to explore crystal structures. And in fact, what we do is we use collective variables that are kind of designed to distinguish different crystal structures. For example, the cell shape, all right? So the 3 cell vectors, these can be different in different crystal structures, all right? Orthorhombic versus non-orthorhombic and different lengths and so forth. What about the molecules? All right, so one possibility that comes from the work of the Parinella group some years ago is to use a kind of entropy created from a spatial distribution, which we just model by a set of Gaussians in distances between pairs of molecules and angles between them, all right? And you can see that if you drive the cell and this entropy variable on this urea crystal, you can actually get this thing to explore different polymorphs on a free energy landscape characterized by these different collective variables, okay? You can also use packing parameters like Steinhardt parameters, which are good when you have, a central unit and then units around it. And these are good for, again, finding, different angular patterns. And although I show it here for an atomic crystal, you can actually create molecular analogs of these by using symmetry related atoms and their centers. And you take these as the vectors that are used to construct these angles and distances. Okay, and that's actually, and then on top of that, you might have to use, internal degrees of freedom, like these torsions. So you have a fairly high number of collective variables, and you want to explore the free energy landscape as a function of this very large number of variables. Now, when it comes to rare event sampling, there aren't that many methods that can explore very high dimensional free energy landscapes. And I think in the next talk by Nishant, we're going to hear more about that, or not the next one, but the one after Ron's talk. But let's talk about how we actually explore these free energy landscapes. So let's suppose you've identified whatever set of variables that you want as your collective variables. So say there's a little n of them. And the problem that you have to solve is to calculate this marginal probability distribution, which is an integral over the phase space of the Boltzmann factor of your Hamiltonian. And then you have these delta functions that say these collective variables should have certain values. And if you can map out this function in this n-dimensional space, then the negative log of it is by definition the free energy landscape. All right, so I think we're going to see this formula a lot probably during this conference. Now, of course, if you want to try to map this function out on an n-dimensional grid, you'll find that for n more than 1 or maybe 2, if it's a real true to force calculation, your ability to do that, it becomes it just becomes extremely difficult because of the dimensional explosion. So the way you want to approach this is to try to sample this marginal distribution. But how do you sample a function whose form you don't know? Well, we're going to do that in a kind of on-the-fly technique within the simulation. So the first thing you would do is to take these delta functions and replace them by Gaussians that are, designed to be very, very narrow and highly peaked. And when a computer, they look a little bit like delta functions. But if you write them this way, then you can take this exponential and fold it into your Hamiltonian. And when you do that, it looks like a kind of harmonic coupling between the collective variable and the S that characterizes your marginal. So the way that you would sample something on the fly to sample this marginal is to extend your phase space, treat this as an additional kind of potential energy term, and add a kinetic energy, a fictitious kinetic energy with some fictitious masses for these S's so that you can actually move them around, all right? Now that'll sample something, but it doesn't actually sample your marginal until you include some additional conditions. And the most important one is an adiabatic decoupling between the fictitious variables and the physical variables. You want to make these S's very heavy compared to your physical variables. Now that will sample the marginal, but it will do so very inefficiently. So the way that we boost the sampling is to introduce a temperature for these S variables that's large compared to the physical temperature, large enough so that you can cross any barriers on your landscape, okay? So your equations of motion for this kind of adiabatic dynamics looks like this. Your physical variables are at physical temperature, and these extended variables, which are just governed by this harmonic potential or harmonic force, are at this high temperature. So let's imagine this is your rough energy landscape and you're going from this basin to this basin. What these equations of motion do are they allow you to cross the barrier easily. So you're sweeping over your free energy landscape. And as you move around it, you're generating more and more information about the free energy surface. What you can prove is that if you take a histogram of these S's, you'll get a marginal distribution called the adiabatic marginal that's related to the true marginal by a power that's the ratio of the two temperatures. So you can see that if you take the log of both sides, that brings down the T over TS factor, or then you can multiply by KTS, the TS's cancel, you have KT log P, that by definition is the free energy at the physical temperature, okay? Now we can compare this scheme that sweeps over the free energy landscape to the popular metadynamics method, which is a bit more serial, right? Metadynamics basically fills a basin with Gaussians that you place down there on the fly. Once you fill a basin, you cross over to the next one, you start to fill it. And as you sum over all these Gaussians, you generate the free energy, okay? So you have to go from basin to basin. The advantage of being sweeping over the landscape like this is one, you can use a very large number of collective variables, and two, as you generate more and more information, you can combine this with machine learning, all right? So as I get, let's say, a sparse scattering of points, I can feed that into a neural network and I can train it. And then, since it's a regression network, it should be able to fill in the missing information for me. So this has actually been very useful for us to run kind of short simulations and then use the machine learning to fill in the missing information. So let me show you an example where we're generating a polymorphic transition in a crystal. This is resorcinol. And it turns out resorcinol has a number of low energy polymorphs that are these three red ones and this black one down here. Now, these are conformational dependent, like our imidacloprid. So the three one up here, the epsilon, the beta, and the P21, are created when these OH groups are in this cis-like configuration, whereas the alpha polymorph has them in this the cis-like configuration. This is trans, this is cis. And of course, the trans configuration is the gas phase minimum, not this one, all right? But this happens to be the lowest energy polymorph, lowest free energy polymorph, all right? And to know that you're getting the right, crystal structure, you can compare PXRDs. And if your force field is good, then you get this kind of match. So you know that you're getting polymorphs that are experimentally realizable. Now here's a simulation that shows that when I start off in one of these upper polymorphs, in this case it was the beta polymorph, and I use the let me come back into this slide. And I use the entropy and the cell variables as my collective variables. And I can actually generate a polymorphic transition from, in this case, beta to alpha. All right. And that has to undergo an internal conformational change, right? So you see that you go from this trans configuration to the cis configuration. This is actually the first time someone's been able to generate this particular polymorphic transformation. And we can get this by starting either from the beta or the epsilon or this P21 polymorph, and it will always go to the alpha one. And there is a large barrier to doing that along this particular trajectory that we have. And you can turn this into a set of free energies at the end of the day, all right? And they're all relative to the alpha polymorph. And you do this at different temperatures, all right? At 0, it's just the energy. But at finite temperature, it's a free energy difference. And the ordering is alpha, beta, epsilon, P21 at most temperatures except the very lowest ones, okay? So we have a set of free energies that we get from a landscape. And what we would want to do is to be able to say, pick 2 of these polymorphs and somehow get the kinetics of the transition from one structure to another. That way you know how metastable a particular polymorph is, and could you use a metastable form for some application. All right, we haven't been able to do that yet for a molecular crystal, but I do want to show you how it works for a simple atomic crystal, all right? So this is another piece of the puzzle, and this is another area where machine learning becomes important. So let's suppose in this case, I have an atomic crystal and it's molybdenum, and I'm interested in the transition, the polymorphic transition between a metastable phase. In this case, it's this A15 phase shown in red, and the more common BCC phase. Now, the A15 phase is actually a phase that's used in molybdenum for spintronic memory devices. And of course, the BCC is used for electronic applications. And it turns out that, A15 is metastable and can convert to BCC on some time scale. So it's not enough to know that these phases exist. What we want to know is what is the barrier to the transition between one phase and the other. Now, if you just run a molecular dynamics simulation, just straightforward MD with an interface between them, which is one way that you can get a polymorphic transition to go, you can see that this is a very, very slow process. All right, and maybe you get a couple of layers to transform from one phase to the other. Now, it turns out that finding collective variables for this particular transformation is extremely difficult. None of the ones that I showed you will work for this, all right? Of course, we know that the difficulty with this problem is, the rough energy landscape problem. But it doesn't mean that I automatically know what the right collective variables are. This is where machine learning turns out to be really important. So let's suppose you've done some kind of, let's say, exploration of the landscape, the free energy landscape of the different phases that you have. So you can use collective variables that I showed you to do that, but it won't get you the right kinetics. So in this atomic crystal, we have the usual phases of HCP, FCC, BCC, and A15. What I want to do is to be able to find a kind of a path from one phase to another through some mechanism. Now, lots of polymorphic transitions may occur on surfaces or at local nuclei or seeds or at interfaces like we have here. So what we're going to do is we're going to use local information in the crystal in order to find a set of descriptors for a machine learning method that can classify these different phases. And a common set of descriptors are those that are used to make neural network potentials. These are the so-called symmetry functions. And they're useful here because they are translationally and rotationally invariant. So for example, we have these Gaussian types where you can tune by this parameter RS where the center of the Gaussian is, and this will be sensitive to maybe the first solvation shell or the second coordination shell of a given atom. Or you have this one, which is similar, but it has a sign that you associate with different regions of your crystal. So once you have a set of, you have a set of descriptors. These are distance space. You can use the Steinhardt parameters for angular information. Once you have a set of descriptors, what we're going to do is to train a neural network to classify the phases based on local structural information. Okay, so by giving it lots of examples of different environments, I can have it spit out for me a probability that a given configuration is in one of the various phases that we have, including mixed phases like interfaces. All right, so here's an example of an interfacial configuration. And what I do is I take these local classifiers, these local probabilities, I average over all the atoms in the cell, and I create a global classifier for a simulation cell that may be pure or may be mixed. In this case, this is the same snapshot showing you BCC and A15 at an interface that may contain other structures. So for example, the global classifier for BCC shows 0.2, and the A15 is 0.52. They don't sum to 1 because you have other stuff in there. Okay, what we're going to do now is we'll train the neural network using a bunch of configurations that are generated from MD at different temperatures, as well as enhanced sampling to get me mixed phases. All right, so I can use all those collective variables that I showed you for the enhanced sampling just to get data for my neural network. All right, and so this is an example of a enhanced sampling simulation of an atomic crystal. It's not molybdenum in this case, but I can generate, let's say, a free energy landscape, and I can see different phases that appear there. And I can use all that information to give me environments for my neural network. Here's my neural network architecture. I've got 11 symmetry functions and 3 Steinhardt parameters, 14 descriptors. I have 2 hidden layers with 25 nodes in each layer, and then my 5 outputs. And of course, because it's a classification problem, this is the cost function I'm using. So that's my neural network. These are the target values. And then you create a test set by siphoning off 125 additional environments, and you get a learning curve that looks like this. And you can see that, you do pretty well for all of the pure phases. So all the different, the 5 phases, and these, this includes disordered phases that we call liquid phases. And then those that are interfacial, mixed phases, it's a little bit harder to get good classification, but even here, the error is less than 0.1. So we have about 94 to 95% classification accuracy, even for the interfacial ones. So then what we want to do is we're going to pick 2 phases that we're interested in, 2 polymorphs. All right, so in this case, it's A15 and BCC. And our collective variable that we're going to use to generate the path between the 2 phases is what we call a path collective variable. All right, so we were inspired to do this by this early work from 2007 of the Paranello group, where they did this in configuration space. We're doing it in the machine learning space, or the space spanned by this classifier vector. All right, so the QI are a set of nodal points that march from one phase to the other. All right, and then what this variable will do is it will sample paths that are foliations of the nodal points. All right, so you'll be able to distort this along directions perpendicular to the line, and you can create different pathways. All right, now this may be a little bit unrestrictive, so we also add in, this orthogonal variable to create a sort of penalty if you get too distorted. Right? And we add that in as a second collective variable or a bias. All right. Now, the reason for working in the classifier space here is that I don't want to have to bias my path by putting in my concept of what I think the configurations should look like as I go from one phase to the other. I want the machine learning to tell me that. All right, so I'm just going to give it environments, and it's going to tell me what it thinks those environments should be classified as. Now I can use this as a collective variable set to drive my enhanced sampling along with, for example, the cell parameters. And when you do that, you can see that you can generate very easily the transition, the motion of the interface between the A15 and the BCC phases. Okay. And not only can you drive one phase into the other, but you can grow the other phase back in. So you're getting statistics on the transition process. Now, if you do this at constant volume, you get a free energy profile that looks like this. And you can see very clearly a barrier for the transition of each layer. That barrier is about 0.5 EV. And although I don't have an experimental number for a system this small, I do have a kinetic Monte Carlo study that tells me that, it's about 0.5 EV to change each layer. So that tells you, sort of what the kinetics are. And of course, if you run this at constant pressure, then you see it's very much downhill from the A15 to the BCC. But each of these little bumps in here still is about 0.5 EV. All right, so about 50 kilojoules per mole. So we see that it's a metastable phase, but the barrier is high enough that you'd expect this phase to stick around for a while, this A15 phase to stick around for a while before you convert to the other. How much time do I have left? Am I probably running close to the end, right?
Yeah, actually, you have already overshot by 1 minute.
Okay, so I'm going to finish up very quickly. I'm going to show you what we're doing for molecular crystals, and then I'll go into questions. So with molecular crystals, not only do you have the packing problem, but you have the orientation problem. All right. So what we're doing is we're creating an additional set of symmetry functions by taking a point vector representation, let's say in a molecule like urea, like this, where you have 2 points in the molecule, and you create a vector between them, and then you take the orientation, the angle between neighbors, and you can create a new set of symmetry functions for orientations. They're modeled on the ones that we use for packing, the G2 and the G3, but these will become additional descriptors for my orientations. All right. And then when we have internal degrees of freedom, we'll take that into account as well as part of our enhanced sampling. Okay, so let me skip over this part and let me just, I know I need to come to the end. So I'll just acknowledge the people who have worked on this, especially Dr. Rogel, who's worked with me on the path collective variable work, and former students of mine who've worked on various aspects of the crystal structure prediction. And of course, the funding agencies, especially the National Science Foundation and our Materials Research Science and Engineering Center, where a lot of this work got started. And so apologize for going over a little bit, but thank you for your attention, and I'll be happy to take any questions you have.
Thank you, Mark. Thank you for a very interesting talk. So I think we have time for a couple of questions. Yeah, Andrew. I saw Andrew's hands raised. So Andrew, please go ahead.
Actually, I think he's just
clapping. Yeah,
he was clapping. He wasn't actually raising his hand.
Yeah, terrific talk, Mark. Really enjoyed it. Thanks so much.
Okay. Yeah. So anybody, if you have,
yeah, I think. So yeah, okay. There is a question.
Jagannath.
Hi, Mark. This is Abhijit.
Okay.
Oh, hi.
Abhijit.
Very nice talk. Yeah.
Hi,
Can you hear me?
Yes, I do.
Okay, great. So I have a question regarding the simulation of the interface you showed. The interface was moving around. And so I just wanted to understand what the free energy means there, because in the actual dynamics of the interface, you're going to have certain types of diffusion mechanisms participating, which causes the phase transformation. And here, there are collective variables. So is there a connection between the real dynamics and this kind of dynamics?
Well, okay, no. I mean, this dynamics, what we're doing is not meant to be any kind of real dynamics, right? What it is intended to do, though, is to get a free energy profile, let's say constant volume and constant pressure. So you can see the difference between the free energy profiles, all right? So this gives you the profile along the S variable in this case. So the simulation you're looking at is not meant to be dynamical, but what we think that we're able to get right in this, very detailed and sort of complicated looking free energy, either here or here, is a set of minima and barriers. All right, barriers. The meaning of the barrier here is the work that you need, or the energy, the free energy that's required to transform a layer in your crystal from one phase to the other. And if that barrier is right, then you can use that to estimate the kinetics of any one of these transitions. All right, and it'll give you a sense of the time scale that over which this interface marches through your system. So that gives you an idea of how long it would take to convert, from one phase to the other locally.
Sure. Okay, thanks.
Okay. Samoni?
Yeah, hi. My question is, much of your analysis depends on the information that you have a priori, the number of phases that or number of stable states that you are going to find. So my question is, what if you have missed something important? So will there be any signature in your calculations?
Well,
that you're missing something.
It's going, yes. So you could. It depends on how important that missing phase might be in any one of these transition pathways, right? Because if I missed something and I don't know that I need to feed that information into, let's say, a training set, then obviously it won't be there when I create this path. Now, if it's a sort of irrelevant phase, then it won't matter. But this, I think, what you're getting at is the importance of being able to explore enough that you've identified all the important phases, and that remains a big challenge. I'm not going to say that we have that solved. That's a structure exploration and structure prediction problem, and that remains difficult. Well, whether or not it's going to influence the pathway between any two phases, is going to depend on, let's say, where on the landscape that might be. Is it close that you have to pass through it, or is it far away that it simply doesn't matter? And you don't know that a priori until you've identified it.
Okay, thank you.
Okay, Mark, we have one more question here and then a couple of questions in the chat box. We'll go through very quickly. Anmol?
Yes, sir.
Yeah.
My question is kind of related to the previous two questions, but I was wondering if this methodology where you sweep around the whole potential surface, can this be applied to biomolecular systems, or because the CVs may not make sense, or the sampling may not make much sense in case of biomolecular systems, or machine learning can actually boil down or reduce the number of CVs which are actually important for a biomolecular phenomena to be seen, is my question.
Good question. So the CVs that we're using are, they're not designed for biomolecules. Obviously, we designed them for crystal systems, but the sampling methodology is general. And as I said, kind of in the beginning, we are working on doing this for biomolecules as well. I just didn't have time to tell you that story. But the idea would be that you can explore structures in a very high dimensional free energy landscape, on a high dimensional free energy landscape. And then let's say you pick two basins that you're interested in. And now we haven't tried, the idea of a machine learning based path collective variable there. So I don't know how well that would work, but what we're trying instead is to model the committer using machine learning. So the committer between two basins is being set up as a machine learning model. And well, you know, as I said, maybe at the next RARE meeting, I'll have more to say about that. But the initial exploration is done using the same basic methodology, but with different collective variables. And I think you'll probably hear a bit about that in Nishant Nair's talk.
Thank you.
Okay, Mark, there are two questions in the chat box. We'll go through them very quickly. The first one is sort of a general question. The question is, I wanted to know about the computational time and complexity of running such an experiment. Probably he meant computer experiment, right? I believe. So,
right.
Yeah.
Well, I mean, it's so system dependent, right? So in this case, you know, the length of our simulation was, I think, on the order of 10 nanoseconds or so, right? To get this interface migration. Generating the training data is not much at all. We do very short runs at these different temperatures, all right? So that's kind of negligible. Let's see, I think I have somewhere on here the range of temperatures that we use. And the training part is not, where was it? The training part is not that long. So we did, you know, 1, 2, 3, 4, 5, 6 temperatures, 6 or 7 temperatures. And we only generate, you know, 170,000 or so atomic environments. So these are relatively short runs on the order of tens of picoseconds, maybe, because MD for crystals is boring, nothing happens. So you just have to generate these environments with different amounts of thermal agitation. Training, not that difficult. That's actually relatively short. So the longest part of this is running this part of it, right? Getting enough data from your simulation to generate this kind of complex free energy landscape. And this is going to depend very much on the size of your system and the computing resources you have. So I can't really give a general answer to that question, but maybe I've given you an idea of what the breakdown is in terms of the different parts of the simulation.
Okay, thank you, Mark. Mark, you could look at the remaining questions in the chat box, and maybe you could also give your replies, okay, in the chat box. I think because we don't have any more time left for this talk. So with this, let us thank Mark for an excellent talk.